So thanks everyone for coming. My name is Seemann, and if you want to know more about me, there's information there on blog.plur.dk. My voice is a little not as it usually sounds. I'm having a bit of a sore throat, so I'm normally wearing a face mask and trying to keep my distance from you. So it's good that you didn't put yourself on the front row here. This talk here is about software development productivity. And in order to talk about software development productivity, I think we need to understand, I think we need to gain an understanding of, what is actually the problem. Because I think a lot of us have had this experience that we're not as productive as we'd like to be, or at least we're not as productive as our managers would like us to be. So how do we address that kind of problem? And I think a major underlying reason for that is that we spend more time reading code than we actually spend writing code. So Robert C. Martin says that it's maybe well over 10 to 1. I don't know exactly where he gets those numbers from, but it's a quote from one of his books, so I'm just going to appeal to authority here. Now, no, just kidding, but I mean, in general, I think this sort of gives, that sort of resonates with me. We spend a lot of time reading existing code, and that means there's not so much time actually left for writing new code. So we can try to illustrate this relationship here with some boxes. So all the orange boxes here are the time spent reading code. There's 10 of those. One green box, that's the time we spend writing code. So usually when you hear people talk about software development productivity, the focus tends to be on writing new code. So you will have vendors, software vendors that will try to convince you that their development environment software is better than the competition, and you will have library authors or language designers and so on trying to sell you their idea so that you can produce code faster and more efficiently. We can try to imagine what that would look like. If we imagine that we have something that is really extremely more efficient than it would otherwise be. If we imagine that we had something that would cut down our code writing time, that would cut it in half, that would be the result here. So this, a 50%, it's 50% reduction in the time that it takes to write new code. This is not at all realistic, but I'm trying to make a point here. So even if we had something that was so radical that basically cut the production time, our writing time in half, that wouldn't really be that much of a productivity gain. It wouldn't be 50%. It would be more like 4.5%. So there's quite a lot of opportunity for improving your software, your development productivity, if you can do something about that readability thing. So that's actually what I have in mind here today. And don't get me wrong, I have nothing against being more productive when writing code. So I'll take the new IDEs and the new smart languages and everything like that. But I also just think that we shouldn't really kid ourselves in terms of that's not really where the improvements are going to be found. We have to find them somewhere else. We have to figure out how to read code faster or make code more readable. I think the latter is more realistic than the former. Okay, so in order to understand, how to make code more readable, I think we need to understand, what actually happens when we try to read code. So here is a piece of code that you haven't seen before, and exactly what it does is not really that important. I'm going to talk quite a bit about this little method here, and it might feel like I'm walking you through the algorithm that we're looking at here, which is actually not the case. I'd rather talk about what happens in the brain when we're reading code. But just if you're wondering, the code snippet here is from an online restaurant reservation system. It's a sample code base that I've written, and but that's not really important. What I want to talk about here is whether or not code like this is readable. And you might look at it and say, okay, so that's not a lot of code. There's only a few lines of code there. It looks like it's nicely indented and so on. So you might think that's readable. And then someone else might come by and say, well, yeah, but it's C#, so that means it's completely unreadable. You know, the curly brackets are all in the wrong places, or it has curly brackets, or whatever else your beef with C# might be. I mean, I'm not assuming that necessarily that you are a C# developer, but I'm assuming you can read code in a language like this. So if you're a Java developer or TypeScript developer, you should probably be able to follow along as well. We can't really have those discussions where, you know, in one corner, you know, someone stands and says, this is readable, and then in the other corner, someone stands over there and says, this is not readable. That's sort of like the kindergarten level of argument there. So we need to figure out, you know, how to, you know, be a little bit more objective about that sort of question. So what happens when we read code? Now, what actually happens is we start a process called, you know, researchers call this cognitive compilation. So it's almost like we're running a little emulator in our brain trying to understand what the code does. And we tend to read from top to bottom. And you know, one of the first things we might you know, discover here is that there's this there's a variable being declared called allocation. And if you are a C# developer, you probably know a list of something is a collection that where you can add more stuff to it, you can remove stuff from it, you can clear it out, you can reorder contents inside of it, and so on. So this is an object that can change state. And when things can change state, that could have an impact on the execution of how a method, you know, decides to run. So if you're trying to understand a piece of code like this one, you say, okay, so this is an object that might change state. I should probably keep that in mind as I'm reading through the next lines of code here, because that might actually, you know, impact what's going to happen further on down. So the next line then, you know, goes into a loop, and you know, you probably know that if you are looping over a collection of things, there's an edge case where there's nothing in the collection, which means you just drop all the way through and we return the collection. That's one option, but that might also be at least one element in the collection, in which case we now start to, you know, do some more work. And again, the algorithm here is really not that important. But what is important is, in this case, we're trying to find a table in the allocation, and if we can't find the table, again, you know, so this if table is, you know, curly brackets, that's sort of like a little C# pun that basically means if table is not null, if table is something, we don't care what it is, but it can't be null. So if it's null, again, we're going to fall through and not really do, you know, the things inside of this this indented code. But if we find a table, we now have, you know, an opportunity to do something about it. And we actually do mutate the state. So we, you know, remove something from the allocation and then add something back. So it's probably fairly clear here is that even if we're changing the state of the allocation multiple times, the number of items that are in that allocation remains the same, because we remove one thing and then we add one thing back all the time. So that's sort of like how that goes. So the point that I'm trying to make here is that there are things that we need to do, and you know, when we read code like this, our brains need to keep track of what it is that's actually going on. And some of you may have, you know, encountered this kind of analysis before, where you're sort of trying to figure out the different pathways through the system that I've tried to indicate with this arrow here. So that kind of analysis is called cyclomatic complexity, which is really a horrible name because it sounds much more fancy than it is, but it's really just counting the number of if statements and looping constructs that you can find. So it's pretty straightforward. But the point of, you know, something like, you know, alternative pathways through the system is that it does give you a sense of the complexity that is involved in the code that we're looking at. And traditionally, we've often used cyclomatic complexity to analyze, you know, just in general, if we're interested in, you know, how complicated is the code. But I think it has an impact on the, you know, how hard it is to read, as well as how hard it is to write. So we can think about, you know, if we have 3 different pathways through the code like we have here, it's sort of like we have 3 different alternative versions of an execution path that sort of coexists as a potential at the same time. So it's like three things that we sort of have to keep track of in our heads. And there's basically one piece of mutable state here, so that's pretty good. So I would say for those reasons, there's only three different pathways that we need to keep track of. There's only really one piece of mutable state that we need to keep track of. I would say that this is something that is readable because it fits in our head. So what do I mean by that? There's research that indicates that we can keep track of about 7 things in our short-term memory. You probably heard about this paper from 1956 called The Magical Number 7 plus minus 2 by an experimental psychologist called George A. Miller. So he figured out by doing a lot of experiments with subjects. He asked people to remember all sorts of things that we can sort of keep track of about 7 things, and above that number we start to forget the first things that we were asked to remember. So that's kind of an interesting insight into the limitations of our short-term memory, and newer research seems to corroborate that story. Newer research actually seems to pull down that number a little bit more. So instead of 7, it might actually be even lower than that. But the point is, short-term memory is really, really constrained. So Miller was talking about. He was trying to make his subjects remember various different things. It wasn't just numbers, but he was also trying to make them remember, names or colors or shapes or whatever else it was. And he called those things chunks. So these were basically chunks of information. So he's saying we can keep track of 7 chunks in our short-term memory. It doesn't have to be primitive values like numbers. It might be pieces of information in general. So there's a little bit of a way out there. But still, we probably have a problem with software development in the sense that there's going to be a lot of things going on instead of just a few things. So I'm just going to start this little animation and just keep on talking. So if you imagine a typical code base, if you imagine a greenfield code base, you might start out with a little wizard that creates a hello world piece of code, and you could say, okay, so that's just one thing that you have to understand in order to understand what that code does. And then you start adding more features to that code base, and it soon exceeds 7. So the question is, what do we do when we have more than 7 things going on? Realistic code bases will probably have 7,000 things going on, or maybe 7 million things going on, and that's not really going to fit in our brains. It's not going to fit in our short-term memory, at least. So we probably need to do something else. So many years ago, I was asked by a company to come in and just help them do a little bit of figure out what to do with their legacy code. So they knew that they had a problem with their legacy code base, but they wanted a little bit of help to get out of that situation. And I had a chance to interview some of the programmers who were working on that code base. And one of them had been in that team for 2 years, so he was the newest hire in that team. So I thought, since he was still fairly new, he might actually remember what it was like to start on that code base. So I asked him, okay, so how long do you think it took you, before you felt that you were able to work on that code base on your own? And he said 3 months. It took me 3 months before I could work on that code base, without help from my colleagues. And what I think happens when we work with legacy code is that we are not engaging our short-term memory. We are using our long-term memory, which is a completely different kind of thing. And then we sort of memorize the structure of a large-scale code base. We can do that. That's not impossible, but it takes time. So long-term memory is quite unlimited in its capacity, but it's slow and it takes a lot of time to actually commit things into long-term memory. It can be really a problem to also remove information from long-term memory. Some brain researchers indicate or have this theory that maybe that never happens. That we never forget things, but we just lose the ability to locate where the memory is residing in the brain. But anyways, what I've tried to illustrate while I've been talking about this is that as we keep on adding more and more things, we can't, either, we have these two options. Either we rely exclusively on our long-term memory, and that's, one of the things that's probably, that slows us down. That means we have to spend a lot of time reading code whenever we want to be, to be able to write some new code. So that's one option. Or we could say, if we could somehow, even if we understand that there are thousands of things going on in a code base, if we could isolate some of them and look at them in isolation, that might actually help. If we could isolate few of them, few enough that they fit in our short-term memory, that would probably help. So, as you probably noticed here, it just keeps on adding random new chunks to this animation here, and it sort of tries to self-organize. So you get this honeycomb-like pattern. So if you imagine that you take out, 7 cells out of a pattern like this one, you might get a figure like this. So this one I called a hex flower because it's just seven hexagonal shapes, seven cells, and a flower because I think it looks a little bit like a flower with the 6 petals and the thing in the center of the flower that I don't know what's called. So we can think of this as just a symbol that's sort of like, if each of those cells is a register where we can put some information, that's, the size of our short-term memory. And one thing we also need to understand is that when we want to look at code, it'd be nice if we could organize code in such a way that, if there's at most 7 things going on in a piece of code that we're looking at, that would actually fit in our short-term memory, and that would make it much easier to read and much faster to read. You wouldn't really need to engage your long-term memory. You wouldn't need to painstakingly use a lot of time trying to understand and learn what this code does. If there's few enough things involved, in an isolated piece of code, you might actually just be able to read it, take a couple of minutes to read it, and then say, okay, all of this actually fits into my short-term memory. I can understand that. So that's sort of like an ideal if we can organize and structure our code in such a way that there's at most 7 things going on. Now, we also need to understand that all software, all code is basically layers of abstraction upon layers of abstraction, and even if you think that you don't like abstractions, you have to remind yourself that the programming language that you're using is an abstraction, and these days it's probably an abstraction on an abstraction on an abstraction. .NET, for example, doesn't compile directly to machine code, so even if you compile your C# code, it becomes bytecode that then later on becomes machine code, and so on and so on. So you're always working with layers of abstraction. So the point is that there will be more stuff going on, even if you try to organize your code so that there's at most 7 things going on. Each of those cells will probably actually contain a new level of detail. So if you wanted to zoom in on one of those cells, there would be more, you would be unraveling or uncovering more details as you go. So we could try to zoom in again on one of those cells and say, all right, there might actually be some code that we could look at. And again, the point of talking about this code is not really I'm not trying to talk you through what actually happens in the code. The purpose of the code is not really that important. What I think is more important is to understand the kind of analysis that I'd like to propose that you do. So this here is a method called create that exists on a class that has the responsibility of talking to a relational database, a SQL Server in this case. And the reason why I chose this is that this represents the lowest level of abstraction, if you will. So if you imagine that you keep on zooming in on various different levels of abstraction in your code base, you can't really get something that is more detailed than this, because there's no more user code hiding behind this. All the objects that are involved here are basically framework code. So SQL connection, SQL command, that's not code that I wrote. That's code that's coming with the .NET framework. And you usually don't go and read the source code for that. So at this point, you're basically at a point where you can say, all right, I can't really go and look at more details here. This is as detailed as it gets in this code base. So we could still ask ourselves the question, is this code readable? And what I'm proposing here again is to say, well, instead of just having this this sort of subjective discussion of whether or not you find it readable, let's try to see if we can come up with some more objective measures. And one of them that I already covered is this idea about cyclomatic complexity. So this is basically counting the number of pathways through the code. Now there's only one branch in this code example that we look at here. If reservation is null, we go one way, we throw an exception. If reservation is not null, we just go all the way through. So the cyclomatic complexity here, the measure of the number of pathways in the code, it's 2. That's very low. So if we imagine for a moment that that's one thing that might tax our short-term memory, and if we use the magical number 7 as sort of like a threshold, we could say, okay, so that fits within the threshold. We're probably good on that account. Another thing we could try to do is to say, well, what if we count the variables? Because one of the things that are important when we are doing this process of cognitive compilation is that we're trying to understand how state might change as the program evolves, as the method executes. Things that might change state are basically, unless you know more about them, you could just count all the variables to figure out, okay, how many things might I potentially need to keep track of in my head, and that's in my short-term memory, in order to understand what's going on here. So we can start counting the variables. It's a pretty simple exercise here. So there's restaurant ID and reservation. Those are 2 input arguments. Then we have something called connection string here, which you can't really see exactly where that's coming from, but that's a read-only property. And if you're not a C# developer, property is just a glorified class field. So this is basically just a read-only class field. And it's a string. It contains some information about how to connect to the database coming in via the constructor. It's not really important how that was assigned. Now we use that connection string to create a con object, a connection object. With the connection object and another string called create reservation SQL, we create another object called command. Now that create reservation SQL there, the one labeled 5, that's another string. It's not a class field. This is actually a constant string. It contains the SQL that's actually going to be executed against the server. But that's it. Once we've counted the command object, there's no more stuff to keep track of. So again, if we're imagining that we can keep track of about 7 things, here are potentially up to 6 things that we need to keep track of. And according to the theory of, at most 7 things in our short-term memory, all of this should actually fit in our short-term memory. So if we're trying to figure out, is this readable in terms of, does this fit in our short-term memory? Yeah, that might actually work. So what I'm trying to do here is to just give you some fairly coarse, unsophisticated ways of trying to quantify whether or not code is readable. And I'm not claiming that this is all scientific. It's more like I've tried this with various different teams in practice, and it actually works pretty well. And there's a point in keeping this unsophisticated, and the point is that this is something you can do while you're actually sitting and working with the code, or if you're discussing things with a coworker. You don't have to pull out a lot of sophisticated tooling and run complicated algorithms in order to figure out is this readable or not. This is something that you can actually just count in your brain as you go along and think about the code. So so I would say that this piece of code that we're looking at here is readable because it fits in our short-term memory. So we can try to enumerate these things, or we might also, if we really want to hammer home the idea, saying let's allocate each of those ideas to a cell in that hex flower thing there, and just to make the point that that code fits in our brain for that particular reason. So I'm using this hex flower thing. You can say almost as a logo for our short-term memory, or symbol for our short-term memory. And I do understand, in reality, it's not necessarily 7. It might actually be, another number, and it's not. It's probably also a little bit fluid. In some cases, your short-term memory may be better than in other cases, and so on. But I'm just keeping this to make a point. What we want to do is to structure the code so that it fits in our short-term memory. The memory constraints that we have in our brain are what they are. We can't really do that much about it. So it would be a good idea to see if we can structure the code so that it actually takes that into account. Now, one of the problems that we have is I started out by showing you a piece of code that is as low level as it gets, that create method that we just looked at. But there's probably going to be some other code that calls that create method. So that's going to be at a higher level of abstraction. So we might want to say, well, if we zoom out, code should still fit in our brain. We would do ourselves a service by making sure that, also at other levels of abstraction, code still fits in our short-term memory. So we need to figure out a way to do that so that, what may have a degree of complexity at one level of abstraction should, when we zoom out, should just look like one thing. Because otherwise, if we have this complexity leak through, we're going to have a problem. So we should be able to arbitrarily zoom in and out of our code base, and ideally, everywhere we look, code should be structured so that it fits in our short-term memory. If we can do that, we can probably make it much more readable. So this should be true at the lowest level. It should be true at the absolutely highest level. So this is the entry point of the application. And again, I don't want to turn this into a tutorial on C# or in this case ASP.NET. But this is basically some wizard-generated code. That's just the main method that starts here. But it fits pretty well in our head because there's not a lot of stuff going on. People who have used ASP.NET will probably know that all the fun stuff happens in the startup class, so we can look at that at the moment. But there's really only 3 things going on, even if we include that startup class as a piece of information. So that's, the entry point fits in our head. So at a very high level of abstraction, it's also possible to write code that takes the short-term memory constraints into account. So if we want to go and look at the startup class, for example, we should be able to do that in such a way where every time we shift our perspective when we're looking at code, we shouldn't have to understand all the other stuff. That should sort of go out of scope. So if I zoom in on startup and I want to learn more about startup, web builder and arcs should go out of scope, so to speak. We shouldn't have to worry about those in order to understand what's going on here. So I'm sort of moving in small steps here. So this is the public API of the startup class. There's no detail, still a very high level of abstraction. But we can sort of try to enumerate, how much stuff is going on here, how much is this going to tax our, mental capacities. And there's 2 methods called configure and configure services. There's a constructor here that takes an iConfiguration value as input, and that's later on being exposed as a property, glorified class field. So I'm not going to count that twice. It's sort of like they go together. But even if I had counted, configuration as a separate thing, that would be 4 things. So in this case, I'm just saying, well, that's just 3 things. So we're still at a very high level of abstraction, but it fits in our brain. So we don't have to use a lot of our long-term memory in order to understand or get a good grip of the situation here. We can basically just roll with our short-term memory and say, all right, I got it. I understand things so far. Let's go and look at configure services. So again, if I want to look at configure services, what happens inside of configure, what happens inside of the constructor shouldn't really matter. I should be able to understand configure services in isolation because it must fit in my, in my brain. If it doesn't, it becomes much more difficult to read. Not impossible, just much more difficult. Orders of magnitude more difficult. Right. So again, we might say, well, is this readable? And instead of just being subjective about it, we can try to quantify it again. Cyclomatic complexity, how are we doing here? Well, there's only one straight line through the code, so that's 1. It's as low as it gets. That's pretty good. If we establish our threshold at 7, we're good on terms of cyclomatic complexity. And I know it looks like it goes on below the screen here, but there's no surprises afterwards there. We can also try to count the things that we might want to, or might need to keep track of if we try to actually, if you imagine that you actually try to understand what's going on in the code here. And there's 6 things going on, just like the other one. It seems like there's a pattern here. But these things are actually things that might change. So if you really want to understand what's going on, how those things relate to each other, you might actually need to keep track of these things as you're sort of running your emulator of the C# code in your brain. But again, since we have the mental memory capacity of 7, that might be just okay. Towards the end here, there's sort of like a little laundry list of things that are being configured, more details here. So the point that I'm trying to make here is that the abstraction level is quite high. So, and even if the abstraction level is quite high, we should still be able to look at the code and sort of understand it at a high level, because at that level there's not a lot of things going on. We should be able to understand it without all of the details. So if you want to know something about how this system is secured and how authorization works, you might then go and say, okay, let's go and read that one. And if you go and read configure authorization, what happens at this level here should no longer be required understanding. You should be able to understand configure authorization all by itself, and that should be no more than 7 things going on. And the same thing goes if you're interested in this configure repository, which is where you have the persistent storage, where that's being configured. You can go and navigate there, and that's going to tell you a little bit more detail about how that part of the system works. But each of those things needs to be isolated from each other, because if you have to remember one thing in order to understand the other thing, that's going to tax your memory, and you'll soon run out of things that you can remember because 7 is the maximum. So we really need to make sure that at all levels of abstraction we can keep the code in our short-term memory. And I would say that that's still possible here. There's not a lot of stuff going on. It's all very high level. It's all very a high level of abstraction. But there's not a lot of stuff that interacts with each other here, so it should still be able to follow. The point that I'm trying to make here is that the first piece of code that I showed you, that create method that talks to SQL Server, that is a very low level of abstraction. This is a very high level of abstraction, but in both cases I've tried to organize the code in such a way that there's not too much stuff going on at the same time. So well, we can try to enumerate those again and say, well, there's not a lot of stuff going on. This is a little bit of an ad hoc enumeration, so I think I'm just going to skip through this. So you might be asking yourself one thing then, and that is, if you have high-level code that calls other code, and that other code will probably call other code again, so there's all those levels of abstraction in your code base. How can we be sure that when we're looking at high-level code at a high level of abstraction that calls other methods and objects and so on? How can we be sure that the complexity that are involved with those method calls and those objects that interact with each other, that complexity doesn't somehow leak through? We really need to be able to be sure that this sort of structure, that we always respect the cognitive constraints that our brain have. So we sort of need to keep that structure at all times. So you might, for example, ask yourself, if you look at this allocate method that we started out looking at, we already established that there's 3 different pathways through here. So that's going to tax our brain a little bit when we are trying to understand what's going on. If we also want to be very unsophisticated and just count all the variables that are involved here, there's actually 6 variables involved, although most of them are actually immutable, so they're probably not going to tax our memory very much. But still, we can understand this at this level. When we're looking at the allocate methods on this level of abstraction, it fits in our head. But on the other hand, if there's 6 things going on here, we can't allow that degree of complexity to escape if we want to look at the code that calls this allocate method. that's not going to work because the code that calls the allocate method will have some other stuff going on as well. And if that calling code should also be structured so that there's at most 7 things going on, we can't allow that degree of complexity to escape to the next level up. So the question is, how do we ensure that complexity does not escape its scope, if you will? And there's a general answer to that, and there's a more specific one. So the general answer is, that's actually the idea behind encapsulation. So the object-oriented encapsulation, the idea of the encapsulation is that you should be able to look at an object and think of it as a single thing. And that means you shouldn't really be, in order to understand how to interact with an object and understand what an object is, you should not it shouldn't be required that you understand the actual inner workings of that particular object. How it's implemented, what the code actually looks like, shouldn't really be important. If you have to go and read the source code in order to understand how to use a method, that basically means encapsulation is broken. So that's the general answer. If you want to make sure that complexity doesn't escape, be good at designing things with good encapsulation. There's a lot of literature about that that can tell you how to do that. Now, with this one, I took a little bit more of a systematic approach to that question. So instead of just trying to be a little bit wishy-washy about, we should have good encapsulation, what I did with this method was something more systematic. So the first thing we can observe about this method is that it has no side effects. So a side effect is something that changes the observable state of your software system. So if you send an email, or if you change, if you add a row to the database, or if you repaint the screen, or whatever else it might be, then that's a side effect. And if you also change a variable inside of your code that then transitively makes an observable change, that also counts as a side effect. But there's none of that here. This is not writing to the console. This is not sending emails or writing to disk or anything like that. It's not performing any sort of I/O here. So there's really no side effect involved in this particular code that we're looking at. So that's one quality that I very explicitly aimed for here. And I also aimed for another one. So I also wanted to make sure that this method is what we call deterministic. So the same input should always return the same output. And we can go back and look at it again and say, okay, so is there anything here that might make it non-deterministic? Am I using any sort of random number generator? No, I'm not. Am I relying on the system clock to see what day it is or what time it is and things like that? No, I'm not. Am I querying some sort of out-of-process resource? Am I querying a database? Am I reading a file? Am I doing any of those things? That actually counts as being non-deterministic as well. But I'm not doing any of those things either. So this method is side effect free, and it's also entirely deterministic. The output entirely depends on reservations and what's in that table's property. From those two inputs, if you will, the output is entirely determined. There's no randomness, nothing, no surprises here. So when you have those two qualities together, you have this thing called a pure function. And pure functions are what we call in mathematics referentially transparent. So what that means is that that means that the function call is equal to its result. So you know this from mathematics, you probably know this from school. If I asked you to calculate 4 times 5, you'd probably just tell me that the answer is 20. You're not actually doing the calculation. If you wanted to do 4 times 5, you would actually have to go 5 plus 5 plus 5 plus 5 and make that calculation. But that's not what you do because you've memorized the multiplication table as a child. And that is because knowing the result is all that matters. How you actually arrive at the result when you have a referentially transparent function is not really important. Because there's no side effect, it's completely repeatable because it's deterministic. So if you know the result, it means that you don't actually have to call the function. So this is important in terms of how things fit in our brain, because that means, from the inside, here's how we arrive at the result. The output, the return value down here towards the bottom is this thing called an allocation. It's an allocation of tables, tables with reservations allocated to them. But once we are at the next level of abstraction, we don't have to care about how we actually arrive at that particular allocation, because this is a pure function. So when we zoom out of this function, we can say, yeah, that's just an allocation, because the function is equal to its result. So even though there was a bit of a degree of complexity inside that function call, when you look at it from the outside, it's just one thing. It is equal to its result, in this case, an allocation. So writing with pure functions is a pretty good way of making sure that complexity does not escape the scope of the method here. So. And if you can't do that, so I'm very, as you may have noticed, I have a Haskell t-shirt on, so I'm quite interested in doing functional programming. If you can't do that, the next best thing is to make sure that your objects have good encapsulation. And if objects have good encapsulation, you should still be able to achieve the result that you could structure the code in such a way that there's not too many things going on at the same time. And that should, be possible to do at, all sorts of different levels of abstraction. So when you zoom in on the code, when you say, okay, so here's a piece of code, now I want to know about some details, further on down, then, that code should be structured in the same way, because you have to respect the cognitive constraints of the brain. They're not going to change. So you should also be able to zoom out, all the way to the entry point of the application, or, anywhere in between. So what we also need to understand here is that if we can do that, this is an ideal, and I'm not saying you can always do this, but if we could, it also means that if we're looking at some arbitrary piece of code that's structured like this, we also understand that, if there's 7 things going on, each of those 7 things that are going on, they count as one thing at that level of abstraction, but they might again have, 7 other things going on inside of them, which is not, supposed to be visible to us from the outside, but we know that that is actually the case. 49 things going on is not, that's not going to, fit in our short-term memory. But again, we know this keeps on, we can pretty much keep on going there, because in each of those 49 cells, there might actually, again, at another level of abstraction, there might be, at most 7 things going on, and so on and so on. So it sort of keeps on going. So this is a fractal, and that's why I, took the liberty of calling this talk fractal architecture, because that's sort of like the guiding idea there. And if you think this is not a fractal, I'm going to show you another one. So this is something called a cock snowflake, which is a very well-known mathematical fractal, where you keep on subdividing those straight lines into adding this little triangular hump on them, and you can keep on zooming in on the edge of this cock snowflake, and it keeps on being fractal. It keeps on having the same shape regardless of how much you zoom. Well, this figure has a level of iterations that it's actually rendered with, but you could imagine that in theory you could keep on zooming, and the same thing is true for this one. I rendered it with four levels deep, because if I add a 5th one, it just becomes one green blob, and that's not interesting to look at. But you can keep on designing a figure like this one. So the idea here is that we should be quite cognizant of the limitations of our short-term memory. The thing about the short-term memory is that it is much more efficient than our long-term memory. Putting something into your long-term memory takes a lot of time. And if you don't structure code in such a way that you can fit it in your short-term memory, you have to rely on the long-term memory, and the long-term memory is slow and inefficient. And that's why we spend a lot of time reading code instead of spending our time, writing new code. But if you can, shift at least some of your code over into having a structure where it's so self-contained that, when you look at it, there's at most 7 things going on, then you will have, code that fits in your head. So that's also the title of my new book that came out, half a year ago, and I have some time for questions and answers, if you will. So I brought 2 copies here. And I'd be happy to give them away for anyone who can, ask good questions. I only have 2, but I'll be happy to answer more questions than 2. So yes. Mm-hmm.
Can you talk about long-term memory and how to become efficient more quickly when you start working with code base, which can be complex and huge?
Yeah, and what is your question?
Do you have any strategies?
Oh, do I have? Okay, so let me see if I get this right, just for people who could not hear. So at the beginning, I talked about, I gave this example of the company where one of the programmers, took 3 months to actually learn a new, to be, able to work for himself in that new code base. Do I have any strategies for learning things better? I don't, but Feline Hermans actually has. So there's a Dutch researcher, computer scientist, who's also been very interested in how the brain works. And she has a book called The Programmer's Brain. And in that book, there is actually various different techniques for learning things better. Some of the techniques that she's talking about are fairly basic memory techniques, like learning things via flashcards and things like that. But she also has some techniques in terms of trying to trace out dependency graphs in code, and so you can sort of have some analysis techniques that she tells you how to use. So that's probably my best answer here. Is that's not really my area of expertise, but Feline knows a lot about that stuff. I'm more trying to figure out how to not get into that situation in the first place, if that's okay. Yeah. So you're saying you're convinced, or you're thinking that the way that I've presented here might actually work. Yeah, I hope so. I mean, so the idea here is sort of like, this is my way to try to explain what I've been doing with various different. I've been coaching various different organizations. That's one of the things that I do. And some of these techniques that I've been talking about here, I started out as being more ad hoc techniques, where I said, when people would ask me, why do you want to do it this way rather than that way, and I started to realize that a lot of it had to do with how much it taxes our brains when we have to read the code afterwards. And then I started to become interested in all that research into how the brain reads and understands and parses things. Unfortunately, Feline Hermans' book, The Programmer's Brain, came out pretty much the same time as mine came out. So at the first, I was a little bit afraid of actually reading her book, because I was sort of like, oh no, she knows a lot about brain research, so maybe what I've written is completely wrong. But they actually, these two books actually complemented each other really well. It's not entirely bogus, I hope, what I've been telling you this far. But I think you should have a book, and I'll take it. I'll be happy to take more questions. And I think I'll take one in the back here, because I don't want to give favorable treatment to people in the front. So sorry for the other guys here.
I'll stand up.
Thanks. There's actually a microphone. It seems. Maybe it works. Oh no.
Then that becomes one item, because my brain can then abstract that out and say, think in the when you're doing SQL stuff, you've got command parameter values, but follow the code above the remaining connection. You break that into a separate paragraph. That becomes a single chunk in terms of what you remember. Say, here's something that happens here. Is that correct? Would you advocate? I mean, I'm an advocate for paragraphs in code, but because it does kind of condense what we remember.
Right. Yeah.
Does that change how we work on that? 5+2.
I think that's, so first of all, I'm actually also in favor of having paragraphs in methods. And sometimes I'm suffering from when I have to show code on PowerPoint slide, there's not a lot of room. So sometimes I remove all the white space inside the code just to make sure that it fits. So the code that I actually copied might actually had a little bit of paragraphs that we didn't get to see here. And it's definitely a way to organize code as well. And if we're looking at code that like I showed you with the SQL stuff, which is basically just one straight line through, that is probably not taxing your brain very much. So the question is more if you're looking at something that has a more algorithmic nature. So Feline Hermans in her book, for example, has a fairly simple example of a little algorithm to turn a normal decimal number into a binary number. Writing it out as binary. If you wanted to write that algorithm yourself, and she actually pretty convincingly demonstrates that even though that is a very simple algorithm, it's actually still hard enough to follow that you probably need to have a little bit of assistance with writing things down on a notepad, besides. And I don't think, putting white space in your code is really gonna help with that sort of problem. Not to say that I'm not in favor of, organizing code, but in terms of understanding, I don't know how much it would work, but you could say in general, if you could organize the code, if you organize the code so that it has several different paragraphs, as you say, you would probably also be able to extract each of those paragraphs into a helper method, and if you can do that, that's each of those paragraphs are probably fairly self-contained already, so that gives you a fair indication of whether or not that's going to fit in your brain as just one chunk, or whether you need to understand the details. I don't know if that's a good answer to your question, but I can't really think of anything else to say. I'm a little bit concerned that if I run all the way down there, that I'm going to get some feedback out. So yes, just to save everyone from the feedback from the microphone, that's probably a good idea. So, but thanks for asking. Now I'm out of books, but I'm not out of time. I have 6-7 minutes yet, so I'll be happy to take more questions. Yes.
So you ran through the process of how to analyze a code to make it readable. Do you have any strategies of what to do next when you run that analysis and you find 9 or 10 items? Is there any particular kind of thing you look for, what to group? Any taxonomy, or these are things I look at.
Yes.
Obvious things to group together and turn
right.
3 things into one.
So you're asking, just for the benefit of the people in the other end of the room, you're asking whether I have good strategies for improving code if the code starts out being too complicated, but you actually want to move in this direction here. I'm quite sure that I have lots of strategies in terms of that's all my refactoring experience. If that's basically what refactoring is trying to do. Not necessarily, if you read Martin Fowler's book about refactoring, he's not saying it like you have to get to 7 things or less. But the underlying message here is that you want to improve the structure of your code. So that's the kind of things that I'm looking for as well. If you want to minimize the things that are going on, you often need to. So I talked about Feline Hermans has this idea about doing some dependency analysis of the way the data flows in a particular block of code, and I think it's probably helpful to do that. And you sort of need to go and take, if you think about what a piece of code does as a graph, there's going to be some sort of dependency graph. you need to take the leaf nodes first, or nip those and try to see if you can move those away into small helper methods. That's a very general answer, but again, there's a lot of literature about how to do refactoring. So, I can't really give you specific ideas because that's an entire seminar, if you will, basically. But I would say when you have the opportunity to extract small helper methods, I would definitely recommend that you look into making them pure functions, because that's really going to help you moving forward. Because if you make a helper method that does local state mutation, well, not local, but if you have these helper methods that pass an object in, they return void, but they pass an object in, and then the helper method does something to the object. That now you have some mutation that escapes that helper method. It's not pure. Now you may you may not have bought yourself anything, because you still need to understand the complexity in the helper method. But if you can somehow make it referentially transparent, it now becomes that one thing. It's equal to its result. So that's at least one thing I would strongly encourage if you have the opportunity to do that. So I hope that was a little bit helpful. Over there in the back, yes?
Testing. Yep.
There's some sound.
Do we have predictable responses to encountering something that's got complexity, I don't know, 10, 20, 500, other than swearing out loud? Do we have predictable responses like fatigue or stress or anger? Is that a thing?
So now you're asking me about a question about psychology, I think.
I think I am. I think the question is more, have you encountered any of that along your way? Not personally, just with others.
Yeah.
I feel I do. I'm just wondering if I'm imagining it or responding badly. Or
it sounds reasonable enough. What I'm again. I've been observing myself, and I've been observing other people over my entire career, and I'm trying to figure out what is it that makes people react positively or negatively to various different situations. And I think this is an overall framework that actually fits pretty well with my observations. I've definitely encountered people being frustrated and having nervous breakdowns and all sorts of things. I'm not sure that it actually has, it has to do with a lot of different factors,
sure,
not necessarily just the code. Yeah. So I think you probably need someone who has more. Again, maybe Feline is probably a better person to ask that question, because really what you need to do now is to say, well, we should try to expose some research subjects to code of various different levels of complexity, and then maybe we could measure their brain activity, or how much sweat they produce while they were looking at the code and things. That's the kind of stuff that she does. But that's not really something that I know much about, I'm sorry.
Thank you, though.
Yeah.
Thank you.
Over there?
When I'm trying to fit a lot of my head that I feel exceeds, the 5 or 7, I start leaning on things like mnemonic devices and metaphors. How does that play into this? Or do we still just stick with? To me, I look at single responsibility and go, well, that's a lot less than 7. But also, you can have one responsibility in a given method or class, and you can exceed your cyclomatic complexity and your number of variables. So, do you ever find you rely on metaphors to accomplish?
Well, so the idea of a metaphor is actually pretty important here, because the fortunate thing, the reason why we can still exist and function as humans is that we can actually, deal with things that are groups of things as though they were just one thing. So George Miller, the author of the paper, the magic number 7 plus minus 2, he calls that, a process chunking. So he says, well, we take a group of things that sort of, maybe we have a metaphor for a collection of things, or maybe we have some other way of thinking of it as being just one thing. and then once we've accomplished that sort of reduction, the complex thing now becomes one thing. So a metaphor is a very effective way of doing that. So you could say again, if you want to explode your metaphor, there's probably going to be more than 7 things going on. But then once you've established the metaphor, now you can think about that, those many things as being just one thing. And that's basically what I was trying to get at here, without using the word metaphor. But that's, I think that fits pretty well with the overall idea. And it's not just in code, and we do that all the time. We think about groups of things as, for example, you are at the moment an audience, which is, many people, but you're just, a single audience, if that makes sense. I'm sorry to be so reductionist here, but I hope that helps you. Yes, sir?
Question. You were talking about code, but SQL statements in SQL code and how we can use this for, because it's the balance between how fast your query or your SQL statement is versus how clean your code is.
I'm not really here. I'm not really interested in execution speed. If that's what you're talking about, I'm not sure that I'm completely getting the question here.
Yeah, so it's like competing with the execution versus how clean your SQL statements are.
Yeah. So in general, I think there's been a lot of people who have said something like this, where they say first make it work. And then do something else. And in the old days it used to be first make it work, then make it fast. And I would probably now at these days say first make it work, then make it pretty, then make it fast. Unless you are in, there might be very specialized situations where you have to prioritize making the code fast over making it pretty. But in my experience, that, again, depending on what your industry is, I've been spending most of my career in what we call the enterprise development industry, and it's less than 10 times in my entire career that I've actually run into something where I needed to tweak performance, because usually, once I've made the code, readable, it also turned out that it was performant enough. So I know we're running out of time. There's another book that came out very recently called Modern Software Engineering by Dave Farley. Dave Farley is one of the people behind this LMAX architecture, high volume trading system in London. And they did some groundbreaking work of making Java run really, really fast. And his experience, what he talks about is that he says, well, the simpler the code is, the fewer instructions there are, and the fewer instructions there are, the less work the CPU has to do, and then the faster it runs. So that's also his general experience with things. So he says there's really you don't have to choose. You can actually usually have both readable code and code that is performant. All right, I'm out of time here. I'm actually a little bit over time now, but so I apologize for that. But thanks a lot for coming.